Welcome today to the third and final introductory chapter video lesson on Year 13 Pure Content. So I've just titled this Subsets of Real Numbers, Representatives and Proofs, like I have for previous two videos. And this video is actually largely the very first bit of actually chapter 1 in the main Edexcel book. But I've just bunched it here along with chapter 0 because chapter 0.1 and 0.2 lead up nicely to this final piece, 0.3. So I've got some warm-up questions for you to attempt first, and then we'll have a look at these very important proofs, which very well could be tested on your A-level final exam. Here are the 4 warm-up questions, so pause the video now, attempt these yourselves, and when you're ready, press play to see how these are done and to just check that your solutions are accurate and correct. Okay, so without further ado, let's have a look at question 1. So question 1, we're told that A is greater than 0 and B is greater than 0, and that both A and B satisfy this equation here, that log A equals log B plus log of A plus B. And for part A, we need to show that A equals B squared over 1 minus B. So this essentially is just harking back to the laws of logs. So we've got log of A equals log of B plus log of A plus B. Okay, so log of B is one thing, and log of A plus B is another. And so logs, because this is log to the same base, log just means log base 10, we can write this here on the right-hand side as a single log. So for A, we can take this and say that log of A must equal log of B multiplied by A plus B. So now, the left side is equal to the right side, the logs are to the same base, so any conclusion for this to be working is that the log of A, so A itself, must be the same as B, brackets A plus B. And so the next step is just to say that therefore we must have a case that A equals B, brackets A plus B. Now we can expand these brackets, so A equals B times A, which is just AB, plus B times B, which is B squared. Now if we subtract AB from both sides, we get A minus AB equals B squared. On the left we can now factorise out an A from all of this, so we have A, brackets 1 minus B, equals B squared. And the final step, we can just now divide both sides by 1 minus B. So therefore, we have A equals B squared over 1 minus B. For part B, it says to write down the full restriction on B, explaining your answer fully. So we've got a partial restriction on B. We're told that B has to be greater than 0. Remember, we can only take log of positive values, so that's fairly self-explanatory, but what else can we say about B? Well, if you have a look here, because A has to be greater than 0, then this whole thing, because A is equal to this expression here must be greater than 0 too, because this is A. B squared is going to be greater than 0, and so 1 minus B underneath must be greater than 0. Okay, because positive divided by a positive will give us a positive. And so the key to answering part B is that 1 minus B itself must also be greater than 0. And so I'm going to just include something along the lines of what you could have written for part B. Something like this. So B is greater than 0, we're given this information here, and because A is greater than 0 too, then 1 minus B on the bottom must be greater than 0, because B squared on the top is greater than 0. And so if we just take this inequality here, and essentially add B to both sides, so 1 is greater than B, in other words, B is less than 1. So because B is less than 1, but it's greater than 0, put these two together, and we have this complete restriction on B. b is somewhere in between 0 and 1, but not including 0 and 1 themselves. Let's now have a look at question 2. Question 2, fairly simple as long as you're careful with these. So put a circle around all irrational numbers in the list below. So surely you'll know that this one's irrational. Pi is completely irrational. Probably the most famous irrational number is. Root 2 is also irrational, and we're going to be proving that it's irrational today. 2/3 is a fraction. Any fraction is a rational number. The square root of 196. Well, maybe this would throw us off, so, you know, it's a warm-up. I'll let you cheat, why not? Let's just try square root of 196. Oh, that's 14. So actually, this is rational. 4 over 16, that's an exact fraction. That's the same as a quarter, that's rational. 1 plus root 2. If you take an irrational number and add it to a rational, we'll always get an irrational answer. So this is irrational too. If pi is irrational, 2 pi is still irrational. 2 root 3 all squared. Well, if we square 2, we get 4. But if you square root 3, then actually that will become 3. So this is going to be 4 times 3, this is 12. So that's a bit of a trick. This is actually rational. This one here is irrational, so circle that one. Minus root 8 is also irrational, that's minus 2 root 2. This here, the pi's will cancel, this is the same as 2, and that's rational. And also here, this isn't root 2, this is a rounded expression for what root 2 is. But this is an exact decimal, therefore it's an exact fraction, therefore this is actually rational. So it's only these 6 you should have been circling, which are irrational. Question 3. Now this will help us to understand the proof that the primes are infinite. So this warm-up question 3 will be, in a sense, revisiting later today. So a student states, adding 1 to a product of the first few consecutive prime numbers will always generate a new prime number. So this student's done a list of the first 3 rows. Seems to check out nicely. Each one seems to be prime 3, 7, 31. Complete 3 more lines of this pattern to show that the student's statement's actually false. So somewhere along the line this is going to fail. We need to find out where it fails. So we've got up to, or she, we've got up to 2, 3, 5. So the next one would be 2 times 3 times 5 times 7, and plus 1 to that. So what do we get? 2 times 3 times 5 times 7 plus 1. That gives us 211. Remember the calculator hack for seeing if a number's prime? We can press Shift Fact. If a number changes, it's not prime. If a number stays as it is, it must be prime. It stayed as 211, therefore 211 is still prime. So the next one, 2, 3, 5, 7. What's the next prime after 7? You should hopefully know it's 11. And again, plus 1. So let's try this. 2 times 3 times 5 times 7 times 11 plus 1. 2,311. And that's prime as well. I'll show you how to check, like I showed you how to check for this one. So again, press equals, Shift Fact, it sticks at 2311, so that's prime. If we go one more, whoops, wrong colour. I'm making a mess of this, apologies. Right, 2, 3, 5, 7, 11, then 1 bigger than 11 is 13, and do that plus 1. What do we get? 2 times 3 times 5 times 7 times 11 times 13 plus 1. That gives us 30,031. Now this looks like it probably is prime, but again, if we go back to the calculator and press Shift Fact, you'll see it's actually 59 multiplied by 509. So for that reason, this isn't a prime number. So it's failed on the 6th row. So because of that, therefore, the student's statement is false. Let's now have a look at the last warm-up question, question 4. Some fairly straightforward calculus. Find the indefinite integral 1 minus 2 root x dx. So, first of all, my advice would always be to rewrite any surds as indices. So rewrite this as 1 minus 2x to the half dx. So if we integrate the 1 or any constant, we just attach the variable to the end, so that becomes 1x, which is just x. Then when we integrate the variable to a certain power, we increase the power by 1, so a half plus 1 is 3 halves. Then we divide by the new power itself. And again, because it's an indefinite integral, we always need to remember to include a constant of integration, so plus c. This can be neatened up slightly, so 2 divided by 3 halves. It looks neat if we call that 4 thirds, so it's x minus 4 thirds of x to the 3 over 2 plus c, and that'll do. So that's a warm-up completed. So let's have a look. We'll just dive straight in to proving some relationships and statements. So get ready now. Let's have a look straight away at worked example number 1. Worked example 1, so proof by contradiction. Prove by contradiction that there is no smallest rational number greater than 0. So I'll just explain what I'm going to do here. I've typed the solutions to these because I've been told my writing can look rather unneat at times. So this should hopefully make it easy to see, and I'll just annotate and explain over. So prove by contradiction. We need to remember from last lesson how to negate a statement. Okay, so I'm just going to flash up on the screen something to remind you from last lesson. So statement types and how to write their negations. So how to form negations. So have a little read of that. Pause the video if you'd like. I'm not going to just repeat what I said last lesson because it might be rather dull and you may well know it. But what I'm going to say here, which I didn't say explicitly last lesson, is if you want to write the negation of a proposition, it's just simply saying the opposite to the proposition. So this here, if I said to you, there's no smallest rational number greater than 0, it's a true or false. It's a yes, there isn't. It's a yes, there is, or no, there isn't. So to negate a proposition, it's always going to be this yellow type here. So we just say instead, it's not true that there's no smallest rational number greater than 0. In other words, we assume that there is a smallest rational number greater than 0. So we go for this type here. So we start by writing the negation. So we assume the negation, and we assume therefore that there does exist some smallest positive rational number. Let's just call it big N. So because n is rational, let the smallest positive rational number n equal a over b, whereby a is an integer and b is also an integer, but just not equal to 0. So if this is the case for n, therefore n will satisfy the requirements of being an element of the rational numbers. N is an element of Q. So this is established now. Now let's consider what n divided by 2 would be. Well, n over 2 would be a over b divided by 2. To divide a fraction by 2, we can just double the denominator. So n over 2 will equal a over 2b. Let's now just consider 2b. Because b is an integer, 2 multiplied by b would also be an integer, because the integers are closed under multiplication. Just going back to chapter 0.1 about closure there. So therefore, because 2b is an integer, and it won't be 0 either, and a is an integer, a over 2b, which is n over 2, will also be a rational number. But of course, n over 2 will have to be less than n, because it's just n being halved. So n over 2 is less than n, since dividing any rational number by 2 will reduce its magnitude. It will halve its size. But this contradicts our assumption that there existed some smallest positive rational number n. No matter what n is, we can always halve it. Well, not just half, we could divide it by 3, 4, we could divide it by any other rational value. So because we just contradicted the negation, the only conclusion via proof by contradiction is that our original assumption must have been false. Therefore, the original statement is true. Therefore, there exists no smallest rational number greater than 0, because we can always find one which is half the size, no matter what we might think the smallest rational number might be. So that's the guideline proof. Copying that down would score you full marks. If your wording's slightly different, that's fine, but the gist of the argument is here in blue. Let's have a look at the next one. Prove by contradiction that there's no greatest odd integer. Again, this is a proposition. Just a reminder of how to write negations. We've got here that there is no greatest odd integer. Therefore, the negation would be to say that actually there is some greatest odd integer. So we start off our proof by assuming that. So, assume that there exists a greatest odd integer. Again, I'm going to call it big N. Let the greatest odd integer, n, equal 2k plus 1, such that k itself is an integer. This is a representative of an odd number. So if k is an integer, if I double that, that makes it even. Any multiple of 2 is even. Then an odd thing will be either plus 1 or minus 1 from an even number. So this represents an odd value. What I'm going to consider now, though, is what n plus 2 would be. If I take big N and add 2 to it, that would be 2k plus 1 plus 2, which is just 2k plus 3. Because big N was odd, big N plus 2 will also be odd, though, because if you take a number which is 2 greater than an odd number, that'll also be odd, because the odd numbers go up in 2s. For example, 7, 9 is odd, as well as 7, because 9 is 7 plus 2. So common sense, but we need to state this in our proof. But of course, this number n plus 2 must be greater than n. It's literally 2 bigger. And so we've just found out the number n plus 2 is another odd number, and it's greater than n itself. But hold on, we'd initially assumed that big N was the greatest odd integer that existed. So we've hit a contradiction now. This contradicts our assumption that big N was the greatest odd integer. Obviously it's not, because n plus 2 is 2 bigger. Because we've got a contradiction, we've therefore proved via contradiction the original proposition. So just conclude by saying that, therefore, there exists no greatest odd integer. Number 3. Prove by contradiction that if n squared is even, then n must be even too. So this is slightly different. This isn't a proposition. This is actually an implication. It's an if and then statement. So which one of these 3 colours does this one fall under? I'll read it carefully. It actually falls under the blue. So if x, where x is any natural or even, sorry, if x is any integer essentially, then if it satisfies case A, where case A is that itself squared is even, then it satisfies case B, where itself is even. So case B is itself being even, case A is itself squared being even. So therefore, we're looking at this one here. So the negation form, just rewording this, is there exists some number x, that satisfies the case A. So there's some number that satisfies the fact that n squared is even, but not that it's even itself. So if it's not even, then n is odd. So the negation is to assume that there exists a number n such that n squared is even, so case A holds, but that n is not even, so case B does not hold. So in other words, we're trying to prove that there's a number n such that n squared is even, but n itself is odd. Because n is odd, let n equal 2k minus 1, where k is some natural number. Okay? So if you take any natural number, if we double that, you get an even, because an even number is just a multiple of 2. Minus 1, or indeed plus 1, will give you an odd, because an odd number is either 1 more or less than an even. Now, let's square both sides. So n squared equals 2k minus 1, all squared. Let's expand out these brackets. That gives us 4k squared minus 4k plus 1. We can now, if we want to, factorise out a 2 from these first two terms. So partially factorising this gives us two lots of 2k squared minus 2k, but then plus 1 on the end. So we've got a multiple of 2 here, so this part's even, but then we're adding 1 to it, so an even number plus 1 makes it odd. So what we've shown here is if n is squared, we get an odd value if n itself was odd. So just writing this down, because 2k squared minus 2k represents a multiple of 2, it's even, therefore that thing add 1 is going to be odd. Therefore n squared, which is this, is odd. But this contradicted our assumption that n squared could be even when n is odd, because we've just proved that if n is odd, n squared has to be odd as well. It can't be even. So this negation can never ever be true. Because the negation can never ever be true, the only conclusion is that the original statement must have been true. So therefore, we've proven that if n squared is even, n must be even as well. Just pause for a second and let that sink in and have a look at what's actually happened. What we actually did is we started with n squared and assumed it to be odd. So we assumed n is odd, and then we proved that n squared is odd. So what we did here is we started with assuming n must be odd, and went the opposite way and ended up with showing that therefore n squared is odd. So we've sort of like done the exact opposite to prove what we needed to prove. So I'm just going to mention this as a side note, which you might want to investigate yourselves if you're particularly keen. So like I've said, that worked example 3. We disprove the negation by showing that if n is odd, n squared has to be odd. So if case A represents n squared as even, and case B represents that n is even, then we can write down this symbol here, A, and that represents n squared not being even. This is the opposite of case A. And the opposite of case B we write like this, and the opposite of case B would be that n is not even. In other words, n is odd. So what we've done here for works example 3, rather than proving n squared is even, therefore n is even, we sort of got around it by proving that if n is odd, then n squared is odd instead. So these two statements, A implying B, is logically equivalent to proving not B implies not A. And this is actually called proof by contraposition. So this is actually outside of the scope of the current A-level specification. If you go on to do a maths degree, it's very likely, not guaranteed, but very likely you'd encounter it. So if you want to have a look at a little clip explaining it fuller, here it is. I'll also put the link in the description, and I'll try and make a little pop-up so you can click it from this video to link to the video I've done on the contrapositive. Don't worry about that. If you're in any doubt whatsoever, ignore anything to do with the contrapositive and just focus on the blue for worked example 3. But this is just a little exploratory optional topic for you if you want it. Let's move on now to worked example 4. Prove by contradiction that there are no integers a and b for which 12a plus 18b equals 1. Now this is actually just a proposition. We're saying, oh no, you can't have a and b for which holds this case. So the negation would be to say, actually, there do exist an a and b such that this is true. So the first start is to assume the negation. So assume that there exist two integers, a and b, such that 12a plus 18b equals 1. Just think about the numbers 12 and 18 and what we can do with those. Well, maybe we can factorise them, and of course we can. We can factorise out a 6. So therefore 6 lots of 2a plus 3b equals 1. We can now divide both sides by 6, so therefore 2a plus 3b equals 1/6. Now you might be thinking, well, where do I go with this? But actually you've got it in the bag here, really. It's just a case of explaining what we found at this step. So just thinking of it carefully and unpicking it. A was an integer, remember? So 2a is an integer too. Z is closed under multiplication. If you take any integer and double it, it's still going to be an integer. So 2a is an integer. Exactly the same argument for 3b. So 2a is an integer, and 3b is an integer. So what happens if you add one integer to another integer? Well, 2a plus 3b, an integer plus an integer, will also give an integer. Going back to the first lesson, 0.1, that's because z is also closed under addition. So what we're saying here, that 2a plus 3b is an integer. However, what we've written here is a nonsense, because 2a plus 3b, an integer we've deduced, which says this equals 1/6. But 1/6 isn't an integer, it's a fraction. So we can say that 1/6 is not an integer. So already you can see here the contradiction. So this statement here we arrived at contradicts the fact that 2a plus 3b is an integer. Because of that, our original assumption must have been incorrect, and therefore there are no integers a and b for which 12a plus 18b equals 1. Worked example 5 and worked example 6, before we get to it, these are the biggies. Okay, so these are the often examined proofs, and indeed worked example 5, you may well encounter an exam question which is an adaptation of worked example 5. So for example, prove by contradiction that root 3 is irrational, or prove by contradiction that root 5 is irrational. They might be asked as well. So take worked example 5 as a template proof for proving that the square root of something that isn't a square number is irrational. This is definitely one of the most important ones you'll encounter. So of course, how to get started with this? Well, saying that root 2 is irrational, that's a proposition. It's a yes or no case. So we assume for contradiction the negation of that. So we're going to assume to start off with that root 2 is actually rational. By the way, before we get started proper, we are allowed to assume, without having to prove it, the fact that if n is an integer, if n squared is even, then n is also even. Very similar to worked example 3 we had a look at, by the way. So we can assume this without having to prove that as well, so it doesn't become like a proof within a proof question. So let's get started. So we're going to assume for contradiction that root 2 is actually rational. Now be thinking, well, what is a rational number? Well, a rational number is anything that can be written as an exact fraction. So we're going to assume here, therefore, that root 2 is a over b, so that a is an integer, b is an integer that isn't equal to 0, and this is the key thing. This is really, really, really important. Assume that a over b is a fraction in its simplest terms. So assume this fraction a over b has been fully simplified. In other words, a and b have a highest common factor of 1. So we're not assuming here that root 2 is maybe something like 2/4. We're assuming it's the fully simplified version. So for example, 2/4 is simplified down to 1/2. So importantly, a over b is a fully simplified fraction. And that's absolutely fair to assume, because any fraction exists a simplified version of itself, yes? So any fraction, if it exists, can be fully simplified. So with this in mind and that established, the next step, we square both sides. So root 2 squared is 2, a over b squared becomes a squared over b squared. Multiply both sides by b squared, we get that therefore a squared equals 2 lots of b squared. And so a squared is even because it's b squared multiplied by 2. So a squared is a multiple of 2, therefore it's even. We can then use this here. So because a squared is even, we can now say that a must be even too. Because a squared is even, a is also even. Now because a is even, we can use an algebraic representative of a and substitute this back in. So because a is even, let a equal 2 multiplied by some integer. So we're going to represent a as a multiple of 2 because we've shown that a has to be even. So let a equal 2k, k is an element of the integers. We now substitute a equals 2k back into a squared equals 2b squared. So we're going to substitute a being 2k into this here. So what we get next is a squared, which is 2k all squared, equals 2b squared. Let's expand this out and simplify. 2k all squared is 4k squared, and that equals 2b squared. If we divide by 2, we can now see that 2k squared equals b squared. So because b squared is k squared multiplied by 2, b squared is a multiple of 2, and therefore b squared is even 2. We can use this thing in yellow again. Because b squared is even, that means b itself must also be even. So we've shown that both a is even and b is even. But think of this, if you have a fraction which is an even number over another even number, that's not a fully simplified fraction. So because a and b are both even, they've got a common factor of 2. And that contradicts our assumption that root 2 equaling a over b can be written as a fraction in its simplest terms. But that doesn't make sense because any fraction can be written in its simplest terms. We've just shown that a over b can never be a fraction in its simplest terms. And if a fraction can never be a fraction written in its simplest terms, it can never be a fraction at all. Because any fraction can be written in its simplest terms. It's so obvious you've probably never considered the fact. So therefore, we've got the contradiction we need to disprove the negation and therefore prove the original statement. We've ended up with a nonsense. So therefore, we've proven via contradiction that root 2 must be a rational after all. Question 6. One of the most famous and, for my money, one of the most beautiful proofs there are. Prove by contradiction that there are infinitely many prime numbers. And this goes all the way back to Euclid, which we use on the thumbnail for Chapter 0. That guy is Euclid, a very famous and important Greek. You do the Googling on that, please. So prove by contradiction that there's infinitely many prime numbers. So we're going to use worked example 3 to help us through the understanding of this. So on your notes, I've split it into 2 halves. So on the left, are like the jottings to sort of build up the understanding of a proof. On the right hand side is going to be the actual proof itself. So starting with the left. So if you just of the mind where I don't really care, I just want the marks, I want to pass. The other side, this side on the right, is going to be the take-home stuff, but I'd like to try and understand what's going on. So if you can have a look on the left as I talk you through it and make notes as you go, that would be great. So, first of all, let's have a look at some specific cases, and then we'll generalize into an overall proof after. So, specific cases. Let's assume the negation. Assume that there are a finite number of primes. Maybe there's only 5. Maybe there's only 1. Maybe 2 is the only prime number. I'm lying, obviously it's not, but just assume that there's a finite number. So, let big P represent the list of all primes you think there are in the universe. So P is the list of all primes. It represents P1, P2, P3, all the way up to the nth prime, where the nth prime is the final prime. That could be trillions or billions of trillions, but maybe we just stop after a while. So P1 is obviously 2, P2 is 3, and so on. So list P is just all the primes that you think exist. Now here's the trick. What we're going to do here is invent into existence this concept of a number big Q. So we're going to take all the primes that exist, multiply them all together, and then the key here is to add 1 at the end. So Q is all the primes multiplied, then plus 1. So because of this, it's worth explicitly saying Q is therefore going to be bigger than any individual prime in P, because Q is all of these primes multiplied together, then add 1 on top. So Q is going to be much larger than any individual prime here. So let's just try a few cases and see what's happening. So what we're going to do here, we're going to consider P, the list of all the primes we know, Q, where we multiply all the primes we think we know together and add 1, but we can ask ourselves if Q is prime or not. So let's imagine that, we're only maybe 4 or 5 years old. Let's imagine we only actually know 1 prime. So let's start with the list P just being 2. Is 2 the only prime in the world? Well, let's see. Multiply everything in P together, then add 1. So that's just going to be 2 plus 1, so Q would be 3. Is Q prime? Well, obviously yes. But because Q is prime, and Q is bigger than P, then list P was incomplete. We thought we had all the primes 2, but Q is prime as well. So 2 wasn't the only prime. We now know that 3 is prime as well. So 2 and 3 are both primes. Therefore, our list P was incomplete, obviously. But let's just see if we can see a pattern going on. So next up, let's think our complete list is now 2 and 3. Imagine just going one step on. Well, Q would now be 2 times 3 plus 1. So Q is now 7. But because Q is 7, ask if Q is prime. Well, again, it is. And again, this disproves the fact we had all the primes. And so if we do this trick by multiplying all of them together and add 1, if the case where Q is prime, that disproves that we've had all the primes. So this is an easy way of disproving that we can have a full list of primes. So 7 was a prime. Next up, let's consider that we knew the first 3 primes. Let's consider we've had 2, 3, and 5. Multiply all these together and add 1, that'd actually give you 31. Again, if you're thinking P is complete, again, this case would disprove that you've got all the primes, because 31, again, is prime, 31 is bigger than 2, 3, and 5, therefore 31 needs adding to our list, so our list was incomplete, we didn't have them all. Go on in the same way, 2, 3, 5, and 7, multiply them together and add 1, we get 211, if that's prime 2. How about 2, 3, 5, 7, and 11, multiply all them together, 2, 3, 1, 1, and that's prime 2. So you're thinking this might seem boring, what's the point of me going on about this? I'm trying to get to the point what happens when we find Q not being prime. So we're seeing here that if Q is prime, that's an easy way of disproving the fact we can have a list of all primes. But of course Q at some point is not going to be prime, like we showed with worked example 3. So imagine we built up a case where P is all the primes we know, 2, 3, 5, 7, 11 and 13. Imagine someone naively thinking that's all the primes there are. We then add 1 to that when we multiply them all together. We get 30,031 like we did in the warm-up. Now that isn't prime. It's not prime because 30,031, the prime factor decomposition of this is 59 multiplied by 509. But this is the beautiful trick of the whole thing. So the prime factors which factorize 30,031, we got 59, that wasn't in the list, and 509, that wasn't in the list either. And let's just think about why this is. So we had Q, which was 2 times 3 times 5 times 7 times 11 times 13. I'm going to write the prime numbers in red. So we had 2 times 3 times 5 times 7 times 11 times 13, and then we added 1 to it. Well, let's imagine this number Q. If we divided Q by any of the primes in P, we'd have a remainder of 1. For example, if we divided it all by 2, that 2 would cancel, but we still have this remainder of 1. If we divided it by 3, cancel there and there, but because 1 doesn't divide by 3, we'd still have this remainder of 1. So what we're saying here is, because Q is not prime, it must have prime factors not already in P, because all of these factors can't be factors of Q, because if you divide this here by 2 or 3 or 5 or 7 or 11 or 13, you still have this annoying 1 in the way. But because Q isn't prime, it means it must divide by something else other than these red numbers. So that's why these prime numbers aren't in this list. So because Q is not prime, it had to be divisible by some other primes not in P, because like I said, Q would have a remainder 1 if divided by any primes in P. So therefore, P is incomplete. So either way, if we think we've got other primes, then this number Q, if we find this is prime, then in that case here, the list is incomplete. Or if we find this number Q is not prime, then because it can have prime factors not in P, again, the same conclusion anyway, the list P is incomplete. So whether Q is prime or not, we're still going to end up with a conclusion that P wasn't complete. So P can never be complete, because no matter how big Q is, if it's prime, the list is incomplete. If it's not prime, the list of all primes is incomplete, so we can always find at least one extra prime not already in the list P. So what we're saying here in the conclusions is the following. So either Q is prime or it's not. If Q is prime, it'll be a new prime not in P, because Q will have to be bigger than all of P. Therefore, P had to be an incomplete list. Or, if Q is not prime, it must have been divisible by some other prime factor not already in P, because if Q were divided by any prime in P, it'd have that annoying remainder of 1. So therefore, there must be some of the prime factors not listed in P. So again, P must have been an incomplete list. So no matter how many primes are in P, it's always going to be incomplete. So therefore, there can never be a complete list of primes, so the primes are infinite. And that's sort of the concept of infinity. No matter how many numbers you can think of, no matter how big you can count to, the concept of infinity is you can always think of number 1 bigger. There's always going to be 1 more. In this case, there's always 1 or 2 more primes you can find. Therefore, there's endless primes, there's infinite primes. So that's like a taster informal proof. On the right hand side now, I'm going to show you the formal proof, which if you copy down, learn and dare I say regurgitate, hopefully regurgitate and understand, you get full marks in terms of any question on this proof of the infinitude of primes. So let's have a look at the main piece. So the main proof. So putting together what we discussed. Assume that there are a finite number of primes and call the list of all the primes big P. So big P is the list P1, P2, P3, P4, P5, blah, 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 all up to the nth and final prime. Now, invent a number Q, which is the product of all primes plus one extra. Then the number Q is prime or it's not. That's an obvious point. Any number is either prime or it isn't. So Q is either prime or it's not. So, first case. If Q is prime, it will be a larger prime than any of the individual primes listed in P. So because Q is going to be a larger prime, it will be a new prime not already in list P. Therefore, list P was incomplete. You need to add in an extra prime, which is Q. Or, what about if Q was not prime? If Q is not prime, then it must have prime factors not already listed in P, because no prime in P can be a factor of Q, because dividing Q by any individual prime in P leaves a remainder of 1 because of this thing attached at the end of Q. Therefore, again, list P must have been incomplete. So either way, you think of it, whether Q's prime or Q's not, we've got an incomplete list. So, this is saying because a complete list of primes P can never exist, our original assumption is wrong. Our original assumption was that the primes were finite, therefore the conclusion is that there are therefore an infinite number of primes. So, it's now over to you lot to try some of these questions yourselves, or question types. So, if you turn to page 21 in the main Edexcel book for year 13, exercise 1A in the pure book, questions 3 all the way through to question 10. Check back in the description if you have any questions or concerns or any comments at all really, and just let me know how you're finding it. Please do consider subscribing if you've not done already, that would be great, and best of luck with getting your head around this proof chapter. So you'll hear from me soon. Take care, study well, and be in touch.